So thank you very much for the nice introduction, and it's my pleasure to be invited here and to present you our work on methods and tools to accelerate image processing applications on FPGA-based systems. And the outline of my talk is, first I want to give you a short introduction and motivation. Then I want to present you our reconfigurable FPGA overlay architecture, which we use in our systems. And then, of course, if you have an architecture, as was just mentioned, also how to design and program it. And there I want to present two tools from us. One is the image processing library using a high-level synthesis approach called HighFlipFX. And the other one is an application and partitioning and mapping tool. And finally, I want to conclude my talk with giving some application examples from our funded research projects where we use those methods and tools, and then conclude the talk and give an outlook. There are many image and signal processing applications. There's still something on the screen. Have a high performance demand. For example, you see here some examples from driver assistance systems or autonomous robots. And on the other side, we want to have a low power and energy consumption to not have to cool the systems, and of course to have a long battery lifetime. And of course, if the systems are working in different environments, they also need to be able to adapt to changing environments and also to get new algorithms for the image and signal processing. Also, if you see how fast new machine learning algorithms are developed, also this way we want to upgrade, of course, a system regularly with new applications and new algorithms. And this cannot be solved anymore by just increasing the clock frequency, because if we do that, as you see in this equation, the dynamic power will also increase. And of course, also the voltage of the system has an influence on the dynamic power. One solution, of course, is to parallelize the system onto a homogeneous multi-core system. But as we also saw in some previous talks, a better solution is to have a domain-specific multi-core system, which is optimized for the application domain, because this way we have a heterogeneous system and we can achieve a higher energy efficiency. So if you have so many architectures, and for example, we have a typical application, like you see here, driver assistance systems to detect cars in the environment, how do we know which is a good platform for that system? And we can choose for a CPU, an FPGA, or a GPU. And this decision, and of course, a combination of those, and this decision depends, of course, on the application. We did a comparison for the applications we are interested in, which are object detection algorithms from image processing. In this example, we use the Akasi object feature detector, and we compared a CPU implementation, a GPU implementation, and an FPGA implementation. Programming language was used OpenCL because it's supported by all three platforms. So we have a common programming interface. And the platforms we use are a Xilinx Vertex 7, an NVIDIA GTX 780, and an Intel Core i7. And you can see from the speedups that the FPGA is the fastest solution for this application, even though the GPU, of course, is also very fast. However, if you look at the power and the energy, the FPGA is the clear winner, having less than 7 times difference roughly compared to the GPU. So what are the pros and cons of FPGAs? So here we see an FPGA platform. We will see that also later, because that's basically already our FPGA overlay architecture, where we have different compute clusters. The pros of an FPGAs are they offer a very high degree of parallelism, on low-level parallelism, and they're extremely flexible, because you're not programming a processor, you're building your own processor. And they can be adapted at design and at runtime, exploiting dynamic and partial reconfiguration, so that we can also update our systems to new algorithms. Furthermore, as we saw, they have a lower power consumption compared to multi-cores or GPUs. The difficulties or drawbacks are and still are, even though there is a lot of work done and there's still a lot of research done in that area, they're difficult to program. So typically they are programmed in hardware description languages like VHDL or Verilog, but those languages are not the languages used by the application engineers who develop the image or signal processing applications. And there exist many C2 FPGA tools, for example, Vivado HLS and others, but mostly they only support accelerators and a subset of ANSI C or C++. Of course, there exist also tools like the one we used in the previous slide, which SDXL, which is OpenCL based, which supports complete design, so not only an accelerator, for specific FPGA platforms. What is dynamic partial reconfiguration? It mainly means that you change a part of the FPGA, a part of the configuration data, while the rest of the architecture stays operative and unaffected. This is very important for image and signal processing because we have the camera data coming into the system. And of course, we don't want to lose any data. So we only want to change maybe the filter, but still keep the frame grabber active. And here's a very simple example. If this would be our FPGA, assuming we have a multi-core architecture on it with different processors connected over network on chip. Partial reconfiguration means basically we can exchange this part here while the communication and the other parts are still operated and not affected. Another advantage of this is, of course, we can use a smaller platform if not all of the parts have to be active all the time, and then reuse it in a timely fashion. This is also termed computing in time and space, basically. In a smaller platform always also means we save costs. So how could we use it then now if we had saw the benefits of the FPGA, but on the other side, also the drawbacks in the programming? One typical approach is to build an FPGA overlay architecture, which makes it then easier programmable. And we saw already some in previous talks, and here I present the one we are using in our system. We basically have a scalable FPGA overlay architecture consisting of several processing clusters, as you see here, connected over a network on chip. Each processing cluster can be selected to have between 1 and 4 RISC-V processors. They have some shared memory, and of course, we can also have either small hardware accelerator together with the processors, or exchange a whole processing cluster with a dedicated hardware accelerator. For the processor cores, we currently are using RISC-V and Ariane cores from ETH. And the system is designed in such a form that each processing cluster, or even just a hardware accelerator within a processing cluster, can be exchanged at runtime using dynamic and partial reconfiguration. To achieve this, we come to the layout we saw on the previous slide. That's why we have this rectangle area. So basically each of these rectangles is one of those processing clusters you saw on the previous slide. And this yellow part here is the network on chip, which connects all of them and allows a communication between them. And this system was implemented on this FPGA platform. So when we now have the FPGA overlay architecture and we can have different processors and accelerators, of course, how do we map our application from the image processing down to such an architecture? For this, we basically provide a design and programming methodology. It consists of different tools, and of course, it's not fully automatic. So some tools accelerate some step, but there's still manual intervention needed. And the idea is that there is a standard called OpenVX for image processing applications that you describe your applications using this standard. You also need a model of the target platform. And of course, we use our HighFlipFX library, which integrates OpenVX kernels to describe our architecture using high-level synthesis. But we'll see that in later slides. Then it goes into an application partitioning mapping tool, which helps us to decide where to place on the FPGA or even if we use FPGA cluster on multiple FPGAs, our designs. We then also can simulate it before we then go to vendor tools such as Xilinx tools. We mainly use them because of the partial reconfiguration and also the Vivado HLS. And then if you want to have a not only reconfigurable, but also relocatable design, we also provide an open source tool called ArmaFlex, which helps to design a relocatable design. So that at the end, we get our partial bit streams, our software binaries for the processors, and of course, also some information for the runtime system, which is a layout and a task graph. But first, have a look at the HighFlipFX library. This allows the user so that they don't have to implement it because it contains FPGA optimized high-level synthesis kernels for typical image processing kernels of the OpenVX library. Besides image processing, we also have neural network functions, and in total, there are currently 66 functions supported. It is very parameterizable. I will give some examples in the next slides, and also highly optimized for high-level synthesis. And the functions basically, as mentioned, are based on OpenVX with some extensions, because for some of our applications like Akasi, we needed some special functions which were not part of OpenVX. It supports auto-vectorization and several data types. So you're not forced to only use 32 bits. You can also use 16-bit data types, for example. And the filters support different kernels, for example, 5x5 or 7x7 kernels. And we have different types of operations. Simple bitwise operation, for example, is shown here, like, for example, arithmetic subtraction, addition. Typical image filter functions like a Gaussian filter, median filter, for example. Of course, convolution is important for the neural network functions, and also image conversion and analysis function, such as to make a histogram. Here you see some results of the library from HighFlipFX. Basically, we compared it with XF OpenCV implementation from Xilinx, and they're put here in relation to each other. So basically, you can see we are always, for those examples, below 1. So we are more area efficient, right? So the dark bars are the flip-flops, and the light ones are the lookup tables used. Here, for example, Sobel and Gaussians, median, and some other filters. But you see here is a standard settings, which we basically use. It's a vectorization of 1, kernel size of 1, and data type of just 8 bits. And then we change one of the values, for example, the vectorization to 8 here, or the kernel size to 7. And this is also possible with both libraries. And basically, then we compare the results from the area. It's good scalable, what we will see in the next slide, and the resource usage is low. We have less functions than XF OpenCV, but we are more flexible, and we provide for our functions more vector sizes and kernel types partially, and also for some more data types. And here you see the scalability shown an example from Gaussian filter. So basically what happens if relative to the standard configuration, which is the same on the previous slide. So how our resources scale, right? So of course, if we get a bigger kernel size, they grow, but as you see here, quite linear, same for the vector size, or if we change the data type to 16 or 32 bits. And HighFlipFX is open source. So if you want to try it out, just let me know. You find it on our GitHub. And there's also a port now of some of the functions to Intel FPGAs. So when we have now our application described in OpenVX and using the HighFlipFX library, how can we then partition it? Because this will give us one graph, but we want to partition it on those reconfigurable partitions or on multiple FPGAs. And for this, we also have a tool flow. Basically, the idea is we have here in task interaction graph, for example, AC stands for different accelerators, kernels from the HighFlipFX library, some input-output from the camera, for example, and this allows us to describe the application. Of course, we also need a model of our target platform on which we want to map on. In this example, we use a model with a network on chip and 4 partitions. And the result of our tool will be basically something like this. So we will have here a mapping. In this case, there will be one master kernel, one processor, which sets up the system. That can also be a hardware implementation if no processor is needed. And then different accelerators mapped to the network on chip. We do the clustering placement in one step. And basically, as this clustering mapping is NP hard, we work with heuristics. And here you see a visualization of our tool. So basically, it tries to map this task graph here, and below those rectangles, that's the platform model. And it tries, of course, to get a good load balancing. So those parts you see here is basically the hardware resources used. And of course, also to reduce the dilation, which means the communication between different components, because then that would result in a communication over the network on chip, and of course, reduce the achievable speed up. And therefore, the algorithm has mainly, 2 parts: load balancing, which tries to make a good placement here, and optimization to reduce then those wires here to place tasks which communicate strong with each other, closer to each other. And of course, to avoid that, you have something like this, here only one task mapped here, and this partition is really full. And for this, the algorithm internally use different heuristics and gradient descent, taboo search, simulated annealing, combined with a parallelization of searching in a search space using multiple threads. And for more information or details, you can also ask me or have a look at that paper here. Of course, we not always have a homogeneous system. We said heterogeneous is important. So we could also have something like heterogeneous tiles or partitions, for example, having different resources like digital signal processing resources or VRAMs on the FPGA, or that could be also a cluster with multiple FPGAs, smaller ones and bigger ones. And we could have an irregular structure like this one, for example. And so both are supported, and what you see here is basically the algorithm scales very good with the number of nodes which we are calculating. So this is the computation time for different task graphs on a 3x3 partition system. So let's have a look at some application examples. So for what we developed, those tools basically, and also the FPGA overlay architecture. One project we are working already since 2017 is Transregio Marie. It's a German national research cluster between different universities. And the goal of the cluster, it's a 12 years project, and we are in the second 4 years, is to have a mobile robot such as this drone, which can localize and characterize materials in sub-millimeter process. And different research works are done in this project. Some are working more on the antennas, on the radar signal processing, on building new transceivers, on the algorithms such as material characterization and localization, using those new sensor elements. And our contribution is the domain-specific computing architecture, which should be then on the drone, and also to make it programmable, of course, and because currently several of those applications are designed using MATLAB, for example. And furthermore, to enable that at the end, together with the algorithms, we can have a real-time material map of our environment. And for this, we developed the FPGA overlay architecture as well as the application mapping tool. Another project which ended last year was about embedded AI artificial intelligence techniques for industrial applications. For this, we also use our cluster, but a bit more simplified because it's an embedded system. As you see here, we use in this example, for example, Pinkboard. And we want to have there more application-specific processors and hardware accelerators. And the target domain are machine learning applications. And that's why the HighFlipFX library not only has image processing kernels, but also neural network kernels. And the use case we use here is autonomous robots. So this is one of our robot platforms, and automotive embedded in the robot operating system. Yes, and with this, I want to conclude my talk and give a short outlook on future work. So basically, what I wanted to present here are a reconfigurable FPGA overlay architecture together with a tool flow for it, because this way we are very flexible as we can adapt both hardware and software at design and runtime to the application requirements, and therefore can achieve a very good throughput by using dedicated accelerators and also achieve real-time and safety requirements. We get a high performance through this because we have an application-tailored architecture, and this also allows us to achieve a high energy efficiency. And the programming support is given by the tools, and we are continuously also working and increasing them. And this also hands me over to the outlook. So the outlook of our work is currently to support further architecture components, to optimize the memory interfaces, for example, in our system, to provide further design methods and tools. And of course, we also are continuously adding new library functions to HighFlipFX. And one of the recent works was, for example, in collaboration with the University in Spain to also test it on Intel FPGAs. And of course, what I didn't mention in my talk are runtime management, because if the system has to adapt itself, some part of the system has to decide when to adapt and also control this. And also there we are working on. And finally, of course, we are always open to evaluate our system with further applications. Well, and with this, I would like to conclude my talk and of course to thank my team, because this is a team work, and I presented works from some of them, which are doing their PhD. Mainly in this example, I had some works from Lester and Ahmed and Nashdad. Thank you. That's all from my side, and I'm open to answer any questions.
That was a great talk, Professor Göhringer. We really enjoyed the talk. Thanks a lot.